Hi students, good morning everyone. Let's continue the chapter called Magnetism and Matter. In this magnetism and matter, in today's session, we'll be focusing more on magnetic field. What's that? Magnetic field. Look at this. Let's start what exactly meant by this magnetic field. In the last chapter called Moving Charges and Magnetism, and in your ninth or 10th standard basics also, you will be getting the term called magnetic field. And this magnetic field is the space around a magnet in which its influence is felt by another magnet or a magnetic substance. It's called the magnetic field. It is the space around a magnet in which its influence is felt by another magnet or a magnetic substance. That's a magnetic field, right? Now, and this space around a magnet will be filled with magnetic field lines, and those are also called magnetic lines of force. Right? These lines of force will represent the magnetic field presence. We'll be discussing about this at the end of the today's session. Let's focus more on magnetic field now. And there are so many other names for this magnetic field. And the names are like this: a magnetic flux density, or magnetic field induction, or magnetic field vector. Whatever may be, it's denoted with the symbol B bar. And it is clearly visible that the magnetic field is a vector quantity. That's the reason I wrote it is B bar. The magnetic field vector, it is B bar. And its SI units I'm writing here. The SI units are like this. It's Newton per ampere meter, or Tesla, or Weber per meter square. Weber is the unit of magnetic flux. Weber is the unit of what? Magnetic flux. About the magnetic flux also we will be discussing in today's session only. What is the topic there? So the magnetic flux in today's session only we discuss. Alright? Shall we focus on magnetic flux density, or magnetic field induction, or magnetic field vector, or magnetic induction? No confusion. Everything represents the same magnetic field. That's it. Ready? Everyone. Now, what is this magnetic field vector or magnetic field strength? That is also the same. Magnetic field strength. What is meant by that? It's so simple. Let's come back to the electricity chapter. There is a charge Q is placed. Imagine it's a positive charge is placed here. At a distance r, I have placed a unit positive charge. That is our test charge. So a test charge is placed, and test charge is always a small positive charge, right? By default, we consider a test charge is a unit positive charge. It cannot be the negative, right? By default, we consider it's a positive unit charge plus 2. At this point, electric field, I'm talking about electric field, right? So electric field at this point will be, this positive charge will repel this positive charge in this way. So the electric field E bar is equal to electric force per unit charge, right? And this electric field KQ by R square. The same way goes for magnetic field also. There is a north pole is considered here at a distance r. So there is a unit positive north pole. What is this? A unit positive north pole. There is no positive here. Positive in the sense it is having positive pole strength. That's it. So unit north pole is placed as a test pole. Here the test charge, here the test pole. So this north pole will repel this north pole in this way. So that is the magnetic field. B bar is equal to magnetic force per unit pole strength, which can also be written as K into, so here K into Q, K constant, Q. In the place of Q, what is this? M, pole strength divided by R square. It's so simple. So here, this can also be written as K value is mu naught by 4 pi. In the last class we discussed. Mu naught by 4 pi into M divided by R square. So finally what I can write? So this is the magnetic field. V bar is equal to F bar by M. So this can also be written as F bar is equal to M into B bar. Remember, this equation will help us a lot in further derivations. The next sessions. F bar is equal to M into B bar. What is F bar? Magnetic force. Magnetic force. M. Small m is the pole strength. Capital M is the magnetic dipole moment. No confusions. Okay, small m is what? Pole strength. And what is B bar? B bar is the magnetic field due to. What is that? B bar is the magnetic field due to a magnetic pole. Isolated magnetic pole. Here, this is just a north pole of a magnet. Isolated pole. Due to this isolated magnetic pole, at any point at a distance r, the magnetic field will be mu naught by 4 pi into m by r square. So magnetic field due to a isolated magnetic pole. So that is a mu naught by 4 pi into small m by r square. Right? What is that? A magnetic field due to an isolated magnetic pole. Okay, so remember these two expressions. Now, for example, here there is a south pole is placed at a distance r. What is this? Plus m. This is our test pole. Okay, that will be always a north pole only. So this south pole will attract this north one with a force, same thing, with a force F bar is equal to m into B bar, only in the opposite direction. That's it. Now, carefully look at the situation here. There is an external magnetic field is kept. External magnetic field is kept in this way. Okay. So this is the external magnetic field, say B bar. Okay. When the magnetic field lines are moving in this direction, what does that mean? So that means that there is a big north pole is available here because magnetic field lines outside the magnet, right? So they move from north to south. Understand? So this is outside the magnet. They move from north to south. So there is a huge south pole is placed here. Imagine a small north pole is placed here. This north pole of the huge external magnetic field's magnet will repel this with a force F bar is equal to M into B bar, where M is the pole strength of this. If there is a south pole is placed here, this north pole will attract the south pole with the same force. F bar is equal to M into B bar. If you want to write, if you want to take, anyway, this pole strength is a scalar quantity. If you want to take, this is plus M because it's a north pole will have positive pole strength and the south pole will have the negative pole strength. If you want to write, you can write minus also. Okay, clear? So this is about when you place the magnetic poles in an external magnetic field. Okay, so I'm writing here a B bar is an external magnetic field. B bar is what? External magnetic field. Now, you know the magnetic field due to the isolated magnetic pole formula. Remember this formula, B bar is equal to mu naught by 4 pi into M by R square. It's similar to the electric field situation. See, for your better understanding, I have just added here, where this K is 1 by 4 pi epsilon naught, isn't it? 1 by 4 pi epsilon naught. But here in magnetic concept, magnetism concept, this K is mu naught by 4 pi, you know, mu naught by 4 pi. So before going to the next slide, what we have discussed is magnetic field vector. It's a vector quantity and its units are written here, Newton by ampere meter. How you got this Newton by ampere meter, you'll understand here. So what is that? Magnetic field. V bar is F bar by M. F bar is Newton. It's a force. Unit of the force is Newton by M. M is what? It's not meters. M is pole strength. Pole strength is a scalar quantity having SI unit ampere meter. Understand? So that's it. So let's move to the next slide. The previous classes we had learned magnetic force and net magnetic force. Here, magnetic field we have just finished and net magnetic field we'll identify now. So net magnetic field. Okay. How the questions will be asked in it. It's simple. Let's take the first example. There is an equilateral triangle is considered. So that is equilateral triangle is taken. A point A, point B and point C is considered here. North pole is taken, north pole is considered at point A and B or at point C and B, any 2 points. Now the question is, what is the net, here I am writing, what is the net magnetic field at C, point C, due to these two? That's a question. So simple. Equilateral triangle, imagine its length of any side is A. Now B net value will be how much at point C? Due to this magnetic pole at this point, because at this point C, we need to imagine that there is a M. So there is a test pole must be considered here. That's what the unit north pole is must be considered there. So then at this point, due to this magnetic pole, what is the magnetic field? So this is the direction of the magnetic field. So imagine it's a B1 bar. Okay. Now, what is that B1 bar? So this is our A. So what is a B1 bar? So B1 bar is equal to mu naught by 4 pi into M. So that is M divided by A square. Right? What is B2 bar here? So the B2 bar will be due to this magnetic pole at this point. So this is B2 bar. So the B2 bar also will be the same. mu naught by 4 pi into m by a square. Sorry, both are same. So when these two are same and the angle between them is how much here? So this is 60 degrees, as it is equilateral triangle, it is 60. This is 60 and this angle will be 120 and this is also 120. Now the net magnetic will be like square root b1 square. So as it is b1 is equal to b2 is equal to b, so what I can write, so b square plus 2b square, yes or no, because b1 square plus b2 square plus 2b1 b2 cos what is angle between b1 and b2, so that is 60 degree. So that will be net magnetic field at the point C will be its cos 60 degrees will be 1 by 2 and this 1 by 2 and 2 cancel. It will be root 3b square. So the net magnetic field will be root 3 into b. Okay, what is a b? Further, root 3 into, what is a b? B is what? Any of these two. So that will be mu naught by 4 pi into m by a square. So that will be the answer. Understand? Everyone. Now, same question can also be asked like this. So that is the class work question. While watching the video, just pause the video and solve this and send me immediately. Last time also, majority of the students have missed sending it. And some of the students have sent this class work after the assignment. It's not like that. Just while watching the video, when you are watching this particular part of the session, just pause the video and do the work and send me immediately. Then go back watching once again. So it is simple. Same equilateral triangle. Here a north pole, here a south pole is considered. That's it. Here two like poles, here two unlike poles. And what is the net magnetic field at point C? That's a question. Question is what? What is the net magnetic field at point C? That's it. Right? Immediately send me the answer. Now, previous KCET exam, the question asked here, that's what we are going to solve now. Previous KCET question. So simple. They have given an U-shaped magnet which is having a north pole here and south pole here. So they have given that the magnetic length. What is the magnetic length? A straight line distance between the two poles. That's called the magnetic length. And they have given clearly the magnetic length is A. Okay. So what is that? Given a magnetic length is A. Question is, this is plus M and this is minus M. What is the net magnetic field at midpoint on the magnetic length? Midpoint on the magnetic length will be here. It's A by 2 and this is also A by 2. Okay, at this point X, imagine, at this point X you need to find the magnetic field. Is it simple? So simple. The magnetic field due to this will be in this way. So imagine that is B of north. Magnetic field due to this south will be in this direction. That is B of south. So the net magnetic field at X, net magnetic field at X will be B north plus B south. Understand? B north. What is B north? magnetic field due to this pole. What is the magnetic field due to an isolated pole at a point due to the isolated pole? What's the formula? So mu naught by 4 pi into m by r square. Here, when you are talking about due to this isolated pole at this point, mu naught by 4 pi into m by a by 2 whole square. Okay. Here also, mu naught by 4 pi into m by a by 2 whole square plus mu naught by 4 pi into m by a by 2 whole square. Okay, clear? So you just solve this, you will get the answer. So this was the previous case question. It's so simple, right? Now, the next topic will be magnetic flux. I'm not going to give you the in detail analysis of the magnetic flux because electric flux you have already discussed in detail. Magnetic flux is same like electric flux. A number of magnetic field lines passing normally perpendicularly through a surface, whatever the surface of consideration, through this surface normally means perpendicularly how many magnetic field lines are passing through it. That's called magnetic flux. As this is the number of field lines, it is a scalar quantity. Okay, and this SI unit will be, SI unit of magnetic flux will be Weber, denoted with the symbol Weber. So CGS unit of the magnetic flux will be Maxwell, right? So there is a relation between them. 1 Weber is equal to 10 raised to 8 Maxwell. 1 Weber is equal to 10 raised to 8 Maxwell. So here, I hope you remember the situation. Electric flux will be E bar dot A bar. A bar is the area vector. So this can also be, we had already learned, electric flux will be equal to closed integral E bar dot ds bar. Same. Magnetic flux will be B bar dot A bar. Magnetic flux can be written closed integral B bar dot ds bar. This can be written magnetic flux is equal to closed integral B bar dot ds bar. B ds cos theta. Okay, this is the formula for magnetic flux. Okay, and this theta is the angle between these two vectors. If B is a vector and ds bar is also a vector, area vector. So this is area vector and this is magnetic field. Angle between these two will be this theta. Understand? So this is, my dear students, let's continue magnetic field lines topic. A magnetic field lines and magnetic field due to a magnetic dipole. Magnetic dipole means a bar magnet. Clear? Because bar magnet will have two poles. There's no existence of a monopole, right? So that's why magnetic field due to a bar magnet. First, let's concentrate on field lines. These magnetic field lines are imaginary, which are first discovered by Michael Faraday, which are also called magnetic lines of force, and these magnetic lines of force represents magnetic field. No confusion at all, they represent magnetic field. Look at the interesting thing. Imagine you have a bar magnet which is having a north pole and south. In the last chapter we had discussed, from the north pole outside the magnet, the magnetic fields lines will originate. And at the south pole, they will not terminate. And at the south pole, they will start moving into the magnet in this way. See, outside the magnet, they move from north to south. Inside the magnet, they are moving from south to north. So, in this way, the first point outside the magnet, they move from north to south. Inside the magnet, they move from south to north. And from this itself, you can understand, and they are continuous and they form a closed loops. They are the closed curves. Okay. Another magnetic field line, let's consider. See here. So this is the another magnetic field line. So did you see that a magnetic field lines are intersecting here? Not only in this diagram, in reality also, magnetic field lines, they never intersect each other. They never intersect each other. So what is the proof that they never intersect each other? This is a commonly asked 1 mark question in your PFC board exams. Why and justify the magnetic field lines never intersect each other, right? I'll just give you the answer. Look at here. So to get the answer, you should know one important thing. At any point on the magnetic field line, if you draw a tangent at any point in this magnetic field gives the magnetic field direction. Gives what? The magnetic field direction. For example, at this point, if you want to draw the tangent, so tangent can be drawn in this way. So at this point, because the field line is moving in this direction, at this point, if you want to draw the tangent you will be drawing this way. This is a magnetic field direction it will give you. Right? How these magnetic field lines are drawn in this way, you may get a doubt. How you have drawn the magnetic field lines are in this way. See, this is the path of the magnetic field line. The curve of the magnetic field line is, I'm writing here, the curve of the magnetic field line is the path moved by a free north pole, in a magnetic field. This is the most important part of this particular field lines concept. If you take an imaginary, or if you take a free north pole, keep it here, it will give one direction. Keep it here, it will give one direction. Keep it here, it will give one direction, one direction, one direction, one direction. All the tangent directions only it gives. If you join all those points, you get the magnetic field line structure in this way. Right? What is that? This is the curve. One curve you consider, that curve of a magnetic field line is the path moved by a free north pole in the magnetic field. So that is the reason how we got these closed curves. Now, our topic is why they never intersect each other. Imagine you have a magnetic compass and focus on the north pole, right? Focus on the north direction. If you keep here, it will show the north direction in the direction of the magnetic field. Imagine the situation, there is another magnetic curve, magnetic field line is moving in this direction. Imagine, now at the point of intersection, you keep the magnetic compass. Actually, according to the definition, in which direction free north pole moves, and that will be the direction of that particular magnetic field. At this point, as there are two magnetic field lines, at each and every point tangent direction it should give. But here at this point, the compass must give two directions because there are two magnetic field lines. Have you ever seen that at a single point the compass will show two directions? Impossible, right? At one instant, tangent means one single direction only the compass can show. When there are two intersecting lines, it must give two directions, but it's not possible. So that's the reason you can conclude they never intersect each other, because at one single point, two directions the compass can never give. Now, so this is also fine. The tangent at any point gives a magnetic field direction. It's fine. And this major part of this magnetic field lines is also done. Now, look at here. See here. One small area you consider, the same amount of area you consider here. Here magnetic flux density is more, yes or no? When more number of field lines are passing through a particular area, that means the magnetic field strength is also more. So I can say at poles, the magnetic strength will be more always. I'm writing here, crowded the field lines. Crowded the field lines, more the strength, more the magnetic strength, more the magnetic strength. Okay, clear? Now you can see inside the magnet there are the field lines which are straight, right? So I'm writing here the sixth point, straight field lines parallel and equally spaced, parallel and equally spaced. We can say, so this is a uniform magnetic field. What is this? A uniform magnetic field. So they must be straight and parallel to each other, right? Even, so for example, if they are curved like this, even equally spaced, so this will comes under non-uniform magnetic field. Uniform magnetic field means in this way, they must be straight, parallel to each other and equally spaced. This is uniform magnetic field. This is non-uniform magnetic field. Okay. Now, seventh point. Seventh point is about magnetic screening or shielding, magnetic shielding. So what is this? It's so simple. Generally, the substances around us have differentiated or are classified into three types. Any substance around you, you consider, they are classified according to their magnetic behavior, classified into three types. Diamagnetic substances, paramagnetic substances, and ferromagnetic substances. Diamagnetic substances, paramagnetic substances, and ferromagnetic substances. I'm writing here dia, para, and ferro. Right? According to the time available, we will be discussing about these also, different types of magnetic substances. But now, the ferromagnetic substances will be more attracted and easily attracted by the magnets. Iron, nickel, cobalt. So these all comes under ferromagnetic substances. So these magnetic field lines will have more tendency to pass through these ferromagnetic substances. So Let's consider there is a iron or a ferromagnetic substance or ring is placed in a magnetic field. You know how the magnetic field lines will rearrange. See here, the magnetic field lines will tends to pass through this ferromagnetic substance. Magnetic field lines will be tending to pass through this ferromagnetic substance. You can see here, they are tending to passing through ferromagnetic substance. Okay, but here you see no magnetic field line passing through this space. That means inside the magnetic field will be zero, right? So this is called magnetic screening or shield. So these are some important properties of a magnetic field lines, right? 1, 2, 3, 4, 5, 6, 7. 7 properties. There will be so many. So whatever are useful for us and those things we have discussed here. So these are the properties of magnetic field lines. I hope it's very clear for you. Now, what was the next topic and the last topic for today's session is a magnetic field due to a magnetic dipole. Alright, see here. First application. We are not going to derive because electric field due to a dipole, you know. There is a bar magnet here. So there is a bar magnet having south pole and north pole. So this is the formula, this is the direction of magnetic moment, okay? And it's a midpoint here. From the midpoint at a distance called D, so there is a point P is placed here. You know, at this point P, what is the magnetic field? That's a question. So magnetic field due to this dipole will be a mu naught by 4 pi into 2m by d cube, because when you consider the short bar magnet, okay, so when I consider a short bar magnet, so what happened to the magnetic field on its axial line? Understand? On its axial line I have got like this, okay. Now, and on its axial line, always in electric dipole case is also same, on its axial line, so the magnetic field we are finding, the magnetic field will be directed in the direction of magnetic moment of the magnet. In electric case also same. So at this point P on its axial line, the electric field will be in the direction of the electric dipole, right? Then minus q to the plus q, here minus m to the plus m. So the next second application here itself we can discuss. Second application. This is the bar magnet of south pole and north pole. Magnetic moment will be like this. From the middle point, exactly at this point, the point P is here. So the magnetic field at this point will be mu naught by 4 pi into m by d cube. So this is the d now. Distance between the middle point of the magnet to the point P. Here, on its equatorial line, this is also a short bar magnet. On its equatorial line, always the direction of the magnetic field will be opposite to the dipole moment of the bar magnet, similar to the electric dipole. Understand? See, the directions also we have to mention, as magnetic field is a vector quantity. Here, the angle between dipole moment and the magnetic field is 0 degrees. Here, the angle between dipole moment and the magnetic, angle between the dipole moment and the d bar, 0 degrees. Angle between the dipole moment and the d bar, it's 90 degrees. You can see here. So here theta is 0 degrees and here theta is 90 degrees. In any other case, for example, you might have discussed this in your electricity chapter. So this is the magnetic length. From the midpoint of the magnet, I have considered my point of consideration P is here. So this is D now, alright? So this is theta. Theta is the angle between magnetic dipole moment and the D bar, alright? So in this case, at this point, if you want to find the magnetic field, the formula will be mu naught by 4 pi into m by d cube square root 1 plus 3 cos square theta. 1 plus 3 cos square theta. You might have learned this or not, but still try to learn this. Mu naught by 4 pi into m by d cube square root 1 plus 3 cos square theta. Even. So from this formula only you get this relation as well as this relation. How? Here you substitute theta is 0. What do you get? Theta cos 0 will be 1. So 3 into 1, 1. Root 4 will be 2. Understand? So 2m by d cube. You get this one. And theta value substitute as 90. Cos 90 will be how much? 0. 0 into 3, 0. So plus 1, 1. So root 1 is 1. So then as it is, mu naught by 4 pi into m by d cube for its equatorial line. Understand? So this is a basic formula you should keep in your mind. Right? Again, once again I am telling you, m is magnetic moment. Theta is angle between position vector and magnetic moment. Okay, so this is about the detailed analysis related to the magnetic field lines and magnetic field due to a bar magnet or a magnetic dipole. Clear? So the next session we will be discussing about potential energy of a magnetic dipole and torque experienced by a magnetic dipole when it is kept in an external magnetic field. Okay, all the very best.